Alright guys, let's start with A-star algorithm now. This is one of the most popular pathfinding algorithms out there because it's said to be more smarter than most of the other algorithms because it gets you to the final node much quicker. Keep in mind though that it doesn't always necessarily find the shortest path, but finds a possible shortest path in the least amount of time by doing more of guesswork and less of trial and error. On the contrary, in Dijkstra's algorithm, we were always finding the shortest path, but that is a much slower algorithm. So, just like in other algorithms, we're given the starting place where we start off. We're given the distance between the nodes, and sometimes we're also given what nodes we are permitted to land on and what nodes or what paths we cannot take. So, every node in A star algorithm has four values: H, G, F, and N. H stands for the heuristic value. This is the estimated cost to move from any given square on the grid to the final destination. This is often referred to as heuristic, which is nothing but kind of a smart guess. We don't really know the actual distance until we find the path, but by using heuristic values, we don't have to look at every node in the grid, and hence it makes the algorithm much faster. So, G is the movement cost, and this is the cost to move from the starting point to any given node on the grid. But this is the distance which is calculated using the path we have generated. So unlike heuristic value, where we don't already know the path in the moment cost or g, we're using the path which has already been generated to calculate the value from the starting point to the given node. Next we have f, which is simply the sum of h and g, and n, which is the previous node that we were on. So at this point, this is as clear as it can get for the definitions of h, g, f, and n. But as we go to the example we'll look at right now, we'll get to know how to actually calculate these values. And once you get a fair idea of how to implement it, even though that's not exactly a part of the A-level syllabus, you'll be pretty much completely clear about the whole concept and what these values entail. So this is the example we'll be using. Here all the red blocks are blocked, which means we cannot use that to reach the final destination. All the blocks which are squared or just outlined are the blocks we are permitted to travel, and the start point is marked in green, which is the 1 comma 1, and the end point is the blue dot, which is 8 comma 10. Alright, now let's look at how we would go around navigating the grid. So our grid follows more of a matrix pattern and less of a graphing pattern. This is common for a lot of AI and ML concepts where matrices are just used extensively. So it's actually a very great, good thing. Alright, so now let's look at the endpoint, which is the blue dot, right? We would first go on noting down the vertical value of it, which is 8, and then the horizontal value, which is 10. Okay, so the endpoint would be written as 8 comma 10. Let's look at this shaded block. The vertical value for this is 5 and the horizontal value corresponds to 4. So we would write it down as 5 comma 4. That's basically it for how to navigate the grid. Now let's move on. So the first step is to find the heuristic value of a node. Now there are multiple methods for finding the heuristic value, such as the Euclidean method, but in this case we're going to be using only the Manhattan method. So let's see what the heuristic value for 1 comma 1 or the starting point would be. So we do this by counting the number of blocks we travel, first horizontally and then vertically towards the endpoint or the blue dot. So if we count these, we will find that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 blocks we must travel. So the heuristic value for the first node would be 16. So we need to go forward and calculate the heuristic value for all of these nodes. To save us some time, I just did that over here. But one important thing to notice over here is the diagonal pattern between the heuristic values. So as we can see, every node that is in the same diagonal line has the same heuristic value. So this would be 16. Everything in this row would be 15. And then below it, we'd have 14, 13, 12, 11, so on and so until we reach 1. And then finally, for the endpoint, we won't have a heuristic value, or it would technically be 0. So just g, or movement cost, are basically dependent on the direction we move in. So we can give a different value or a different cost to every direction that we go in. So if we were to go up, down, left, right, this would have one cost, or if we were to go diagonally, we can give this a different sort of cost. Now, there is one important thing to note. There is one thing I'd have you note is that there are different definitions for movement cost across the internet, and there are different versions of the explanations for this. But the version that I'm explaining right now pertains to A levels, and it might not be the exact same definition other people would use and implement. Here we're taking a triangle with sides 10, 10 and 14, approximately 14, and going up or down in this direction, or going right and left would have the movement cost of 10, but going diagonally would have a movement cost of 14. That is basically what this triangle we've made here explains to us. And this is put down in a much more simpler way over here, or how you would look at a map usually, where this would be north, or us going up, south, west, and east. And this would be northeast, this would be southeast, this would be northwest, and southwest. Okay, so now let's assign cost values or movement cost values to the first node, which is this. So if we were to go diagonally, we'd have a movement cost of 14. If we were to go up, which we cannot in this case because there's no block up, it would be 10. Down would also be 10. And right and left would be 10. So a zoomed up view of that is right here. Okay, this is the same thing that I've written over here, but zoomed so it's easier to understand. Here's an important thing that you need to know, that movement cost values don't stay fixed. They might change when you consider values for other nodes. So over here we select the first node, which is this, and then we select the second node. So a zoomed up view of both of these cases is explained over here. Here we have it for 1, 1, and this is for 2, 2, 2, 1. In the first case, you can see that the movement cost over here was 10, but in the next case, it's 14. So this is just a simple matter of, I would say, perspective from going one node to the other node. Okay, so let's start finding the path now. Starting at 1, 1, the first path that we can take is towards the right. We can go to the next block, which has a h value, heuristic value of 15, and a movement cost of 10. You can find these heuristic values in the table before. Now when we add the heuristic and movement cost values, that gives us the value for f, which in this case, if we go towards the right, the value of f would be 25. The second path we could take is going diagonally downwards. That would have a movement cost of 14, because going diagonally gives us a cost of 14 as we discussed before, and coincidentally the heuristic value is also 14. So this would give us the total f value to be 28. Path 3 would be going downwards. So if we go downwards, the heuristic value is 15 and the movement cost is 10. So this would give us the f value of 25. If you're confused how we got these heuristic values, look at the timestamps in the description and go to the one that says heuristic pattern. Over there, you'll see how we got 15 and 14 as our heuristic values. So now we have these three paths. Path 1 and 3 have the least value for f, which is 25. Since 25 is lower than 28, we can take either path 1 or path 3. Assume that we took path 1. We would have moved from 1 comma 1 to 1 comma 2. Now at this point we have to figure out what next moves are possible. So from 1 comma 2 we can either go towards the right, diagonally downwards, or just down. So I've written these paths down over here in the form of coordinates. So from 1 comma 1 where we started to 1 comma 2 and then we go to 1 comma 3. That would be our next node. Then we could go either diagonally downwards as well, that would be 2 comma 3, or we could go downwards, that would be 2 comma 2. So guys, now we move to the next node, starting from 1 comma 2, and these are the paths that we have. We will begin by calculating their f values, and we would do this by combining their h plus g values. So for the first path, if we were to move to the right, and that is take path 1 as in shown here, the heuristic would be 14 and the g value will be 10. So that would give us 14 plus 10, which is 24. If we were to take path 2, which is going diagonally downwards, our heuristic value would be 13 and our g value would be 14. This would give us 27. For path 3, which is moving downwards, our heuristic value is 14 and our g value is 10. So again, the total would come to 24. So out of these guys, we again have to select the paths with the least f values, which would be path 1 or path 3, which has the f value of 24. So we could take either of these two paths, but not the second one. So now we have found two paths, and I'll show them below here, and we'll see the paths that we have taken and their total cost, the total f cost for traveling from 1 comma 1 to then to the next node and then to the third node, right? So our current path treads 3 nodes. Alright, so the cost of going from 1 comma 1 to 1 comma 2, which is our first and second node, is 25. Now this is the lowest value we had below before, so we're selecting that. And next, if we were to go right from 1 comma 2, as I showed you in the previous slide, that would have a cost of 24. So our total f cost, or our total cost of traveling the path yet, is 49. And as you will see now, let me get the next one. If we were to go, this is if we were to go down after going to the second node. The cost of going from 1 comma 2, which is from here to here, was also 24. And since the total f cost is still the same, we could have taken either of these two paths. But if we were to go down diagonally instead, like this, taking this path, the total f cost would be 52. Now guys, since the f cost is higher than the other ones, at this point I'm not asking you to discard this part totally, because when we are calculating our final paths and reaching the final destination, we'll probably make better use of this path. I'll show you an example of this pretty soon. So before, we directly took the path from 1 comma 1 to 1 comma 2, and that was going towards the right. But we did have another option back then, which would have looked like this, where we could have gone downwards, and this would have been the path from 1 comma 1 to 2 comma 1 and then to 2 comma 2. Right, now if we were to take this path, Let's just calculate what would have happened. So the f value of going from 1 comma 1 to 2 comma 1 would have been 25, and then going from 2 comma 1 to 2 comma 2 would have been 24. The total would give us 49 once again. Now this is the same as the ones we had in the previous acceptable or paths with the least f values before. So again, this is one of those paths then we can take. But there would also have been an other choice where we could have gone directly from here diagonally upwards. But we don't want to do this because by doing this, we'll be going further away from the destination. And we could have also, somebody could have also thought that we can go further down here. But that's not an option, right? We cannot go further down or diagonally downwards. We actually had only two moves starting from here that was going towards the right or going diagonally upwards. But if we go diagonally upwards, that's away from the target. So we stick to the path that treads toward the target, which is going to 2 comma 2. So from before, these are all of our three acceptable paths. All of them have an f value, a total f value of 49. And since f values for all of these are the same, the system will repeat itself. It will repeat the same process on all the corresponding nodes going ahead till it reaches the destination. The path with the least f value will then be chosen. And this will be the shortest path. Now, this is the guessed shortest path. So, a difference between this algorithm, A star algorithm, and Dijkstra's algorithm is that A star algorithm will guess the shortest path. This is not guaranteed to be the shortest path. But the reason we use A star algorithm is because it's much faster than Dijkstra's algorithm. And just to stress on it again, it will guess the correct path, guess the shortest path, but it might not be the shortest path. So remember before I asked you not to discard paths because they had a greater f value at that time? But now since all of our paths are leading us to this point, we have a more direct path, right? That we discarded, we thought of, had the choice to discard earlier, but we didn't. Going directly from 1 comma 1 to 2 comma 2. Now the f cost of this would be as follows. First we add the h value and then the g value. Since we're going diagonally downwards, the g value would be 14 and the h value would be 14. So this would give us a total of 28. Now it's amazing that the path we could have discarded before because it had a higher f value at that time is now giving us a path towards the target in a much significantly smaller f value, right? So if I bring up those other graphs, just give me 1 second, you'll see what I mean. So here they are, right? We are reaching the same point now with a much smaller value of f. So this can be considered as one of the paths we would have a chance to tread. So now let's look at all of our choices in one glance, okay? So this looks like a pretty promising option. We had a few more. So now if we were to compare all of these, the first one, which is this, would clearly have the upper hand over the other two. This one, the ones with the values 49 over here, these two. As in just two moves and in a significantly lower f value, which is 28, we can reach the same point. But comparing the other two, if we look at the first one over here, the one below, we can see that it goes away from the target, right? And so the first one would have a clear advantage because it's direction is towards the target. Now, the second one, what we would do here is just like we realize now that 28 would have been the better choice. When we go forward and find out this whole path that will probably go like this or something, we will be able to compare this first one and the second one. So if we were to continue this whole matrix, the sequence throughout the whole matrix, we'll find a path that brings us to the target much quicker. Now, during implementation, the definition of G or the moment cost is what is the total F cost that we have, the total F value up till here, or summation F that as I wrote it before. But for A levels, we don't have implementation as a part of the syllabus at this moment. So it's not important to know what we would have to do to implement this algorithm in code. And guys, since A star algorithm doesn't offer backtracking unless our movement costs are fixed, there is no guarantee of finding the shortest path. So guys, to end with, this is how probably one of the most efficient paths for this specific matrix would look like and a result that A star algorithm might produce.